My name is Chris, and this is day 10. Actually 11, but I'm doing day 10 of Advent of Code. And I don't have my GPT intro. And that's okay. As you can see, I'm getting started a little late. I cherish my sleep on Saturday nights. And so I did not do AOC last night. Not really going for speeds. That's okay. But I'm going to catch up and do a doubleheader tonight. I'm going to do both day 2 and day 11. So let's jump right in. Day 10, pipe maze. You use the hand glider to ride the hot air from Desert Island all the way up to the floating metal island. This island is surprisingly cold, and there definitely aren't any thermal to glide on. So you leave your hand glider behind. Dang it. I really like that hand glider. You wander around for a while, but you don't find any people or animals. However, you do occasionally find signposts labeled hot springs, pointing in a seemingly consistent direction. Maybe you can find someone at the hot springs and ask them where the desert machine parts are made. The landscape here is alien. Even the flowers and trees are made of metal. As you stop to admire some metal grass, you notice something metallic scurry away in your peripheral vision and jump into a big pipe. It didn't look like any animals you've ever seen. If you want a better look, you'll need to get ahead of it. Scanning the area, you discover that the entire field you're standing on is densely packed with pipes. It was hard to tell at first because they're the same metallic silver color as the ground. You make a quick sketch of all of the surface pipes you can see. The puzzle inputs. So the pipes are as follows. This is a vertical pipe, north and south, east and west, 90-degree bend, 90 degree, 90 degree, 90 degree ground. S is the starting position of the animal. There's a pipe on this tile, but your sketch doesn't show what shape that pipe has. So I'll have to figure that out, I'm guessing. Based on the acoustics of the animal scurrying, you're confident the pipe that contains the animal is one large continuous loop. For example, here is a square loop of pipe. If the animal had entered this loop in the northwest corner, the sketch would look instead like this. Right, so we know there's an S, which is the start, but we don't know which of these it is. So we can infer that based on two factors. We know based on the S, when we figure out what the loop is, we'll be able to see and say, okay, what's the two connecting nodes? And then based on that stack, we can infer which one it is. So in the above diagram, the S tile is still a 90-degree F bend. You can tell because of how the adjacent pipes connect to it. So I just said. Fortunately, there are also many pipes that aren't connected to the loop. This sketch shows the same loop as above. In the above diagram, you can still figure out which pipe forms the main loop. They're the ones connected to S pipe. Those pipes connect to pipes. Those pipes connect to, and so on. Every pipe in the main loop connects to its two neighbors, including S, which will have exactly two pipes connected to it, and which is assumed to connect back to those two pipes. Here's a sketch that contains a slightly more complex main loop. Here's the same example sketch with the extra non-main loop pipe tile. So this one is where starting here, you go down, you go right, down right, you go up left or left up, then you go right, cross, up, pick left, up, okay? Because it's based on a connection direction. So depending on if you're coming from which side depends on, okay? Yeah, cool, got it. If you want to get out ahead of the animal, you should find the tile in the loop that is farthest from the starting position because the animal is in the pipe. It doesn't make sense to measure this by direct distance. Instead, you need to find the tile that would take the longest number of steps along the loop to reach from the starting point, regardless of the way around the loop the animal went. In the first example with a square loop, you can count the distance each tile in the loop is from the starting point like this. So 0, 1, 2, 3, 4, 4, 3, 2, 1, 0. So really, we just need to figure out the total loop length and then divide in half. We don't really need to know what the midpoint is. 4, here's a more complex loop again. Here's example 8. Yeah, because it's like 16 steps to go around the entire thing. Find the single giant loop starting at S. How many steps along the loop does it take to get from the starting position to the point farthest from the starting position? All right, cool. So we've got two test inputs. Let's get their more complex versions. So in this first example, okay, we'll grab this one here and copy this input, and we put it in our test file. That's our test input, and then we're going to go and create a test2, test2.txt, and then we're just going to go in and grab the second input in its current form, or its more complex form, I should say. And then we'll go ahead and add that one as 8. So what we're doing here, let's talk through the solution real quick. So what we're going to do is, if we go to our inputs, we're going to find the S, which is here. It'd probably be better if we look at it in the AOC view, because it's spaced a little bit better. We're going to look through this input, and we're going to find the S, and then we're going to look in all 4 quadrants. So up, left, right, and down. And we know that if there's a dot, that's ground. And if there is a pipe, depending on which direction the pipe is, will dictate, first we can go in, but then also we can go out. Now we know that one of these 4 is going to be valid, but we got to make sure that we can ingress from that side, and then we can also egress from that side. So that's going to be the complicated bit. We know that the pipe can receive something from to the left or to the right of it. So if it's coming from X, it can receive from X, or vice versa. And so we'll have to figure out how we're going to do that. And then similarly, when we go down, in this case, you can see these pipes allow, and then we're just going to have to keep doing that. We're going to do like a recursive loop so that we add things to the stack. So S will get added to the stack, and then pipe, and then L, and then so on and so forth. And as we're adding to the stack, we'll eventually complete the loop. I'm going to do one other thing here too. I'm going to create a common folder, which I should have done way earlier. And that way, when I look at day 4, we know that our input, we want a matrix of strings. So we want a slice of string. So what I'm going to do is common dot yeah. So that way I can create an as string matrix function that receives a string and returns back a slice of string. And then I suppose we can leave them as strings, but in this case, I don't want to. We really need a delimiter in here as well. So a delim, which will be a string as well. So we can actually notate it like this. That's interesting. I do like the fields operator in here, and we're going to do this if sep so what I'm doing is I like that new fields function, and I'm probably going to hate myself for doing this later. I really should have a separate function. Yeah, let's do this instead. We're going to leave this as is. I don't like it. Well, I want to use the fields one where we have white space, and I will actually We'll do this. The idea here is we're going to create some helper functions. So as we do these problems, it's a little bit faster. So fields as string, don't need a separator. And we just do them as two separate functions. And the reason is I just didn't like that other implementation. So we're not going to print. We don't need to print here. Oh, and this should be line. Same thing here. Missed that almost. Okay. So now we can, in our main program, we can do common.asString matrix, and we can pass it a string and we can pass it a delimiter, which in this case, the delimiter is going to be empty. And that should give us back yeah. Okay, perfect. So now we've got our slice of string strings. So now we can operate on this. So what's our next step? Well, we need to find the start. So our start is we're going to have to loop through all of them, and we're going to have to get the one that has a letter S. We'll just create a function for it. Returning, really we want the X and Y, or the start position. So we can do a for we'll return something out of bounds if we don't have a start. And so get start, we'll call M, and that'll give us our XY. And we'll do %d, %d, y, comma x. Cool. So let's run that. We should end up with 1, 1. Okay, cool. So if we look at our initial input, we'll look in the AOC view, 1, 1 is right here. So 0, 1, and then 0, 1 downward. So we've got 1, 1. Okay, cool. So now we've got everything into a matrix, and we've got our start position. So from here, so we're going to do something interesting here. We're going to pass in our matrix. We're going to call move. We're going to pass in our matrix. And then we're going to pass in our position. Let me call this. I don't know why I inverted these. It's fine. That'll be all right. So we're going to loop. We're going to move through, and we're going to pass in our matrix. We're going to pass in our current position. In this case, our destination. We don't want to be in a loop, so we're going to create a map called visited. I'm sorry. It's going to be a map of string to bool. Okay, and then we're going to set visited equal true. Okay. So we're moving from here to whatever the next is. This is our starting position from when to visited. So our twos will be y plus 1, x plus 1. Nope, we won't do plus. Minus 1. This should be x. Jeez. Jesus Christ. Okay, so let me move this out. So the reason we have a visited map is so that we don't reprocess the same node over and over again. We want to process it once, and if we somehow get into like an internal loop and come back. So let me kind of explain. Let's go here. So we're gonna have, let's do with this. If we have some nodes on a grid, right? And we want to figure out what the longest path is, we may check something like from here to here, and then from here to here, and then from here to here. But we also want to check from here to here, and then we're also going to check this path from here to here, but also from here to here. And so we want to make sure that we're not getting into a loop situation. So we always mark a path visited so that we don't visit it again. Although I don't know that it's necessarily going to be a problem here. But what we're doing is we're saying move from the position I'm in to this next position. And we're doing that for each of these. And so yeah, make that true. Loops, 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 loops. And then we'll go and then we'll do func move, and we'll do our matrix, which is our string from x, from y, to x, to y, which are all ints. Yeah, ints. And then our map string to bool. And then our dest x and dest y, which are ints. Right. Cool. So now that we've got those, now we need to do some maths. So let's look at our possible moves. Okay. we'll just bring this right in here. So a couple of things. If 2x or 2y, or probably should make these capitals, make it easier to read. Yeah, if 2x or 2y So we know that if we're outside the bounds of x and y, that we shouldn't move forward, or that we can't connect to anything because there's nothing there that's valid. So we go ahead and exit. The other thing we know is that if 2x is greater than length, or 2x is greater than the length of m minus 1, or 2y greater than the length of m sub 0 minus 1, so we'll get that first record, then we want to exit. So we know we can't do anything in that condition. I don't want to do this. Let's force habit. Okay. Return nil. Then we need to make sure that, so let's look at this. If we are at position 1, 1, then there's only a few pipes that we can handle. So let's start with this simple. Let's talk about up, down, right? So if x is our row, so if we look at our input, our x is 0, 1, 2, 3, 4, or yeah, our x's are going this way, right? Our y's are the position in the row. So we'll start first with, there's only 4 directions we can head. We're never going to get into a situation when both the from x minus the 2x and from y minus the 2y, if we do this correctly, are ever going to conflict, or rather, are they both going to adjust at the same time? We could theoretically talk about that, but we're not going to worry about it. So let's just implement the vertical pipe first. So there's only 2 scenarios. We can say if 2x minus, let's start with the from x. From x minus 2x, so that's going to be your up and down movement, equal to 1. So that means we're going to either go up or down, and m sub, so if it's positive 1, that means we're going upward, because the from would be our 1 index, and then the 2 would be a 0, which would be above. So if it's a 1, we're going upward. So we need to check if that's true. Actually, we could do it this way instead. I think this will read easier. Okay. Yeah. So if nx equal to 1, nx and y should be no different, but we'll just go with it, equals to pipe. Where are we at? Where's my pipe? So this means that we can move. So what we're doing is we're taking our current, and then we're taking our 2. We're determining whether or not the 2 location is movable, is valid because it matches the certain pipe that we're looking at, right? So for instance, we know that we can go to that pipe because we're validating it before we're moving. So that's good. So if that's true, we're going to go ahead and set visited always anyway. Right. So we always set it. And then pipe. Then we're allowed to move. So then we're going to go ahead and initiate a move. And we're going to move. And it's going to be 2x and 2y. This is just the diff, not the actual diff x, diff y. And so we know that we can 2x plus dx. So we'll use it here, and then we'll do 2y plus dy. Although dy is not changing, it's going to be 0 in this case. Visited is true. And then dest x and dest y. So, all right, so that's visited. Let's see here. If we go negative on the x, meaning we're going up, this is also valid for the pipe. So let's see what else is valid for up. So up is connects south and west. So 7. So let's do this then. Just make this easier. We'll call this just C. And then we'll do string dot strings contains and the string we're looking for has a pipe in it. That's what we're going to have. And then our character is this. And then this will be 7F. Okay. So we can, if we're going up, we're going from the south and we're going west, south and west, or east rather. And then pipe is either north and south. So connecting south and west. Okay. And then there's no other south in here. I suppose we could also do, this would be C. We'll do that for simplicity. And then we could also say if C equals a period, return nil. Yeah. Okay, cool. And then all of that is good. So I think that covers that. So, okay, so let's talk about the negative case. Connecting north and east. So that's L, north and west, L and J. So we could do the same thing here, but it's -1 and then it's L and J. Okay, so then I think let's just go ahead and look at the difference in Y. So if our difference in Y is a 1, meaning that we're going from the west to east, we have this, and then I think it's J and 7. Yeah, because we're on the west side and we're either going north or south. So it should be J and 7. So this is where we're on the east side, and we're either going, so it's F or L. Okay. The last thing you want to do here is, if it's a node we've already seen, return nil. Okay. So, all right. So that'll keep us from reprocessing. The only issue we have left is okay. So what this is going to do is this is going to build a stack of everything that's in the loop from beginning to end. So that we end up with a single, essentially a line, if you will, or all the XY coordinates based on what the valid moves are. And then what we need to do is, let's go ahead and we're just going to add a bool to this. And we're going to return false here, and false here. How do I want to do this? All right, so the problem that we have is I don't know how to tell if my loop is actually connected. So I can build these loops, I can iterate on these things until we've reached a visited node, but it's not clear to me that we actually made it back to our destination. I know what my dest x and my dest y is. I suppose what I can do is I can say if 2x equals dest x and 2y equals dest y, then let me just think about this. When we're checking to see if we can move into the next pipe, we don't care. But a 2x can always be, if it's dest x, then we're there. So yeah, this is true. So what we'll do is we'll just return on the last iteration of our stack. We'll just return the destination. Okay, so that'll end our loop, presumably. And then, yeah. We'll call this north, south, east, and west. And then we don't have to do any appends because I don't really care about this. Yeah. Yeah. So we'll just put them in a stack and then we'll check each one. So there are two things we're checking for: length and if we won. So the way we're going to check to see if it won, so we're going to loop through in winner range of winners, and we're going to say if winner sub 0 sub 0. So the first one on the stack, the first index on the stack, equal to X, and the last one on the stack equals, then it's a contender, and then we'll say if loop, if length winner greater than length loop, loop equals winner. And then finally, it'll be length of loop divided by 2. Wow, you like that? All right, don't need the score. I'll return no. All right, let's go for broke. Index out of range 0. So we want to go up. So this should be minus. This should be plus, I think. Yeah. All right. Let's give our input a shot. That's right. Awesome. All right. Wow. That took a little bit of debugging. Let's do a little bit of a recap. All right. So let's talk about what hung me up quite a bit. It was just the direction and the flow from each of these pipes that took quite a bit of debugging. I probably should have functionalized this a little bit more and did individual tests for each. Hindsight's 2020, but it pretty much works as follows. We start by creating a matrix. I created a helper function for that. And we create this map of visited nodes. That's to make sure we don't revisit nodes over and over again. So once we get to the end, we'll be at the end. I just said, hey, we're going to create a recursive function And when we start at S, that's our starting point. We find S, the X and Y, and we iterate through each one. And we simply just say, go up, go down, go left, go right, from that starting position. And each one should populate a winner of some list size that is greater than or equal to nil. We'll look at the move function there in a second, but that's a recursive function that we call over and over again. I think to simplify, we could actually remove the destination. I don't think that was used in our solution, so let's go ahead and just do that. We'll get rid of the destination in here, and then we'll get rid of it here, all of these locations here as well. We'll do a quick little multi-line magic there. We'll run this again just to make sure. Yeah, 7173. All right, awesome. So let me we'll refactor that out. So going back to the move function, the way the move function works is it takes in what the from XY chord is, and it gives it a 2XY chord, and then has this visited map to make sure we don't recursively visit something over and over again. Although, again, I think in this case, the only one is really the S that we have to worry about. And then what we're going to do is we're simply just going to, if we're outside our bounds of what the matrix is, we're going to go ahead and exit. And then we're going to check our direction, essentially. So whether or not we're going up, down, left, or right. And depending on which direction we're headed, the character that we're on dictates what we're moving into. So that's how we solve this. And we increment accordingly. So if we're coming from the right and we have a pipe, we want to go left, which is to -1. And that's pretty much it. We have this little helper function to get the start. So that's part one. Man, that took a while. All right, as always, over and out.